So, ladies and gentlemen, allow me to start the afternoon sessions and allow me to introduce Professor Stefan Maier. First of all, a few words about his life. He graduated from the California Institute of Technology. After graduation, he moved to start academic career at the University of Bath. And in 2007, he started with Imperial College London. Now he is chairing nanophotonics in the physics department of this Imperial College. And he is also co-director of the college's Center for Plasmonics and Metamaterials. It means the main research interest of Professor Maier is plasmonics and metamaterials. And in 2010, his work on nanoplasmonics was recognized with the International Seckle Prize for the Physical Sciences, the Peterson Medal of the Institute of Physics, and the Fellowship of the Optical Society of America. So, thank you. The floor is yours.
Great. Thank you very much. Thank you for the nice introduction. So I'm really honored to be here, and it's actually a particularly nice start of the week for me because I'm speaking here today at the opening of your wonderful Nanotechnology Center, and tomorrow we are going to have the 5-year anniversary of our much smaller scale London Center for Nanotechnology that I want to tell you a little bit about. And then probably we won't do any work anymore for the rest of the week. But so we have just heard very nice introductions to some of the large-scale facilities that Ceitec might cooperate with. Now, I will scale down a little bit. So I'm not from a large center, but from a university, from Imperial College London. So what I want to do in my talk is I want to outline some of the nanotechnology research that gets done at our university. I want to tell you how we built a Center for Nanotechnology in London, some of the possibilities for collaboration, and then also a little bit about my own research and about some of the exciting possibilities of nanotechnology, particularly for those of you interested in optics and in light. So just a little bit on the history of Imperial College and where we are. So it's a fairly young university, just about a little bit more than 100 years old, and it's right in the center of London here. So you can see the campus here. For those of you who know London, this is Hyde Park here. It's all very compact, which brings its own challenges if you want to have large-scale nanofabrication facilities, large-scale characterization facilities, and of course the other challenges. Nobody on an academic salary can afford to live anywhere nearby unless you are the rector who has his own house right here. So it's a mainly technical school, so we have the natural sciences, engineering, medicine, and a small business school on this campus here, and I'm located in the Department of Physics. It's a fairly large department, one of the largest in the countries, and we really cover almost all areas of physics. So like you can see all the different groups here. I'm associated with experimental solid state. So this is our building here. We have a relatively decent intake of undergraduates every year. So like you can see the stats here. It's large, as I've told you, so 115 academics really working in about all areas of physics. Many of them actually working in nanotechnology. What we are particularly proud of is that we, over the last couple of years already, have a fairly high intake on female undergraduates. You can see the numbers here. And also quite a lot of our graduates end up doing a PhD or end up in finance in the city, even though we don't advertise that these days anymore so much. But many of our graduates actually get lost, as we say now, to the city of London. Now, what is very important for a place like ours is to have international collaboration. And of course, we do that at the level of one-to-one collaborations with scientists, at the level of memoranda of understanding with major institutions. And I was very pleased to hear that there is actually significant progress in having a memorandum of understanding between Imperial College and Ceitec, which hopefully can get finalized later this year. But a really other good way to increase international exposure and bring in international blood into the university is via master's programs. So we offer quite a large number for such relatively small universities of one-year master's programs in like all of these areas that you see here. Now, one of the keys for also financial sustainability, of course, are also interactions with industry, particularly as funding from research councils dries up more and more. So the physics department alone in the last couple of years has had about 13 spin-outs companies. We have a dedicated industry club, which basically provides a framework for companies to come to open days, to sponsor students if they want, to start collaborations, and basically to just take advantage of the expertise that academics offer. And a lot of the work that we do for industry is in the area of nanotechnology. I just have two examples up here. So we have one successful spin-out company that makes nanostructured solar cells. So like what you see here is an example of a 3.5 gallium arsenide solar cell, and this has a nanostructure on it, which led to this solar cell having the world record for a single junction solar cell up to a few weeks ago. And also we have a number of spin-out companies in the areas of optical sensing. Now, a couple of years ago, we did something that you will probably call Ceitec Light, so our own Center for Nanotechnology, which is actually, after I listened to the introductions this morning here, it is very much a model similar to Ceitec. So it's also a collaborations of universities. It's not its own legal entity. In our case, it's Imperial College London, where I'm from, and a little bit farther to the north, University College London. The whole project got started about 10 years ago. The official kickoff was almost 5 years ago, so tomorrow it will be 5 years. It's the London Center for Nanotechnology. It also has its dedicated building, where a number of the people that are associated with the center work, and it has pretty much the same philosophy as here. So integrating scientists working on the hard physical sciences with scientists working in biology, in bio-nanosciences, and in chemistry. Put them all under one roof, have very good nanofabrication facilities there, and this way also have a rather large pool not only of scientists working there, but also of students' intake. So, like you can see some of the fields here, and I think I invite you to go to the webpage to find a little bit more about it. One of the particular challenges there, of course, was to establish such a hub in the center of a big city like London, both in terms of transport and in terms of sheer space. So. And what the mission of the center is really is to apply nanotechnology to the main challenges that a society faces. And we have subdivided that into 3 topics here. One is planet care, which really looks at exploiting nanotechnology for clean, green energy production, for example, for new, safe fabrication processes, for catalysis, and so on and so forth. And other one is healthcare, so using nanostructures for diagnostics, for example, and also using nanostructures for therapy. So these might be magnetic nanostructures, these might be fluorescently tagged nanostructures. I will tell a little bit more about that. And then the third area, information technology, which is closer to what my own research is about, which I'm going to tell you in a moment. So there it's really all about how can we move from microelectronics basically to nanoelectronics, and in my case, from microphotonics to nanophotonics. So it's really these three areas here. And I want to show you now one example of applying nanotechnology and actually quite a fundamental research to the area of photonics. Yeah? So what can modern technology, what can modern nanofabrication, as will be possible here at Ceitec, do, particularly if you are interested in the science of light, so to speak. Now, over the last couple of years, over the last 3 years actually, we had very good reminders why photonics, after you might very well say that the 20th century was probably the century of microelectronics with computer chips and all of that, but in the last decades it's been really photonics that has also been one of the biggest driving forces. And one reason we have here, we just had 2 years ago the 50th anniversary of the laser. Yeah, you find everywhere now, of course. And also 2 years ago, there was the Nobel Prize for glass fiber optics. And of course, take those two together, and what have they enabled? They have enabled the internet. Yeah? And like what you see at this graph here, and I always still find it quite amazing. It shows you the number of distinct users of the World Wide Web over time. I hope you can read it in the back, but we are somewhere now, well, almost hitting 2 billion distinct users all of the time. Yeah. So, that is really due to the fact that photonics has really driven the technological development over the last couple of years or so. So now the question that we are after, and actually quite a large grouping now at Imperial College, and of course also at many other places, is can we do something similar that has worked so well for microelectronics to photonics? Can we make structures smaller? If we can make them smaller, we can make them faster, and ultimately we can make them cheaper. Yeah, with the hope, as a famous rock group put it 10 years ago or so, to make us all fitter, happier, and more productive. And of course, this has worked very well in microelectronics. Yeah? So this is stolen from the Computer Science Museum here in Silicon Valley, just reminding us all of the really big feat of going basically within 50 years from one transistor to about 500 million transistors on a computer chip. Yeah? So typical size dimensions of transistors in modern chips, as you will all of them find in your laptops, are on the order of 10 nanometers, even less for gate oxides. So now one would very much like to do that also with light, so with so with fiber optics, for example, or with solar cells. Yeah? If we can control light from the micron level, which is on the order of the wavelength of light, to the nano level, then we can make more efficient solar cells. We can vastly increase the density for optical data storage, for example, and also we might be able to see structures that are much smaller than the wavelength of light with a light microscope, for example. But of course, there are two stumbling blocks, and one of them is the diffraction limit of optics, which basically just tells us that we cannot focus light down to a size that is much smaller than its wavelength. Yeah? So we just get basically not a very sharp point, but we get a shape like you see here. Yeah? And then also, of course, we have to live just like anywhere with the elements that nature gives us. Yeah? But there is actually a nanotechnological solution to the problem of controlling light at very small length scales that is very, very old. And you can see a very nice exponent of that in the British Museum in London, actually, and that is stained glass. So this is a glass cup from Roman times. It looks like this in transmitted light. It looks like this. This is the same cup in reflected light. And the staining is due to the fact that this glass consists very small particles of gold and silver. And these very small particles of gold and silver provide a way of concentrating light on the nanoscale. So what we see here in this little movie here, this is a computer simulation of two small silver particles close together, and I illuminate them with light, and they show how the light gets concentrated to the surroundings of the particle. So the main message is that using nanostructured metals and modern nanotechnological fabrication techniques is we have a way of confining light on the nanoscale. And the science behind that, and that is one area of nanotechnology that has really grown rather explosively in the last 10, 15 years, is called nanoplasmonics. Nano, I guess the name is clear, and plasmonics, because the fundamental excitation in these particles that gives light to this nano focusing is called a plasmon. So one thing that you see here, these are now single particles that are created using a process called electron beam lithography. These are very small silver particles, and also Ceitec here will, I think, have a number of such facilities available pretty soon. And these silver particles are illuminated with nothing more but white light. And we look at how they scatter the light, and you see, well, they look nothing like normal silver looks like. Yeah? So depending on the shape of these particles, we can concentrate either blue light, we can concentrate green light, yellow light, red light, and so on and so forth. Yeah? And it's then this light concentration very close to the surface of such a metal particle that we really think can revolutionize the science of light. Yeah? And then, using modern nanofabrication, one can then move away from just having single structures like that to much more complex-looking metallic nanostructures that you see here. So metals that are now also structured on the scale of tens of nanometers. So basically on a scale that is commensurate with the size scales of modern nanoelectronics in computer chips, which might hence provide a way to build this elusive interface between nanoelectronics and the new nanophotonics. And then at the same time, also new techniques to actually actually look at these light fields with very high resolution have become available. So at Imperial College, we work on a large number of topics surrounding this in our Center for Plasmonics and Metamaterials. So some very fundamental research, the solar cell research that I've already told you about, some research where we try to combine such structures to increase the resolution of magnetic resonance imaging, MRI, and then also some efforts on large-scale nanofabrication and many others. What I want to advertise here already is that there is already one way of very easy collaboration with us and actually with many European partner labs in the area of bio-nanotechnology and bio-nanophotonics. We are chairing a network by the European Science Foundation that I just want to advertise here. You can see the webpage here. The Czech Republic is a member of it, so Jiří Homola from the National Academy in Prague. He's the local contact point here. And this provides a very easy way for staff exchanges from anything from a couple of days to about 6 months, I think, is the maximum. And it's a completely open network, so it's open to anybody basically working, in the bio-nanosciences. So if you're interested go to this webpage here. So now I just want to finish up my last couple of minutes with giving you just a couple of technical examples without going into any detail, how we can use this nano localization of light. And in the first part, I just want to show you one extremely simple application in nanometrology. So an example from the hard sciences. So what we are after here is, let's say you have a material that can undergo a phase change. So we don't have to care what the material is here, but it is vanadium dioxide. And if we heat it up, its crystal structure changes. So if you make a thin film of it and you heat it and you cool it, you can see a difference in light transmission. Now, nanoplasmonics provides now a very easy way to take this process to the nanoscale by simply putting gold nanoparticles from solution onto the surface of such a material that you want to investigate. Then you look at the scattered light. You can see a small light dot here of this gold nanoparticle. You again heat the material and you cool the material, and now you can trace out the phase change on the nanoscale. So the local phase change just in the rounding of this gold metal particle. Yeah? So a very simple way of how we can use a metallic nanostructure as basically a nanosensor. Yeah? It changes its color when the surrounding changes, which in this case here is a phase change. And other example here that brings us together with the biosciences is to use metallic nanostructures for sensing. So one principle here, for example, is if you have one metal particle and you have a field enhancement around it, if you push another particle close by, you can get an extremely high field enhancement right in the gap here. So if you link these particles by the right molecules that can give off a lot of light, then you have a very efficient light source here. So with a quite neat trick, we made this into a sensor. We chose this molecule here, not so that it gives off efficiently light, but that it gets cut in half by an enzyme, by a medically relevant enzyme that we want to sense. So basically, as we put the enzyme in here, this gets cut in half, the field concentration drops, and the light emission from our molecule started to drop. So by just looking at the change in light emission of that molecule, one can sense concentration. And now what I just want to show you at the end are some other quite interesting applications of such photonic nanotechnology based on metallic nanoparticles, where we not only use the fact that by controlling the shape we can change the color, but actually by controlling the shape with relatively simple physical processes, we can also control how this excitation decays. And it can decay in two ways. The light field that gets concentrated can either just heat up the particle, so the particle gets hot, or it can get re-radiated into light. Yeah, that's why we saw these nice colors of metal particles. And now, in playing with shape, one can now tailor the balance between the two. And like here are some applications that are coming out of this. So this is work, for example, that gets done at a cancer center in Houston, where metallic nanoparticles get used for treating tumors. Yeah? And there the idea is that the metal nanoparticles get brought close to the tumor, they get illuminated at the wavelength where this light concentration happens. The light gets concentrated, the particle heats up, and it introduces cell death around it. Like another application that you can see here, you might recognize this if there was a line through it. This is basically a miniaturized old-style television antennas. Yeah? You can probably still see them somewhere here in the countryside as well. You certainly can in Germany, but you see here the longer reflecting element, and then here these direct elements. Yeah, now the length scale here is 200 nanometers. So this is a television antenna for a single molecule. So if you put a single molecule or like a quantum dot nearby here, this metal nanostructure can redistribute the radiation into a given direction that you would want to. And like a last example is, so like we have, for example, one European Union project where we put metallic nanostructures on solar cells in order to use the light concentration to make solar cells thinner. Here's another example that I want to quickly show you. Just to show you the sensitivity in these changes in colors. So what we show here is a light transmission spectrum through a structure that looks like this. It's a small disk. It's a very small gap, and it is surrounded by a ring. And if we just put a single layer of atoms on it, in like this case a single sheet of graphene, then we can see a distinctive shift in the light transmission through these units. Yeah. So the like main message is that metallic nanostructures such as this, that modern nanotechnology applied to metals opens up a whole new playground for the science of light on the nanoscale. And now, just in my last 2 minutes, what I just want to point out, one of the really nice aspects of this field is also that it brings together students from very different areas. So like not necessarily just from physics, but also from electrical engineering, material science, chemistry. Simply because nanoplasmonics really has the potential to be applied to all areas of science and technology where light is a prominent ingredient. And like there's even something in there for mathematicians, and I just want to end with that now. So like this is a pretty neat challenge, I think, here. So like what we wanted to find out is what is the shape of a metallic nanostructure that is at the same time small, but it can concentrate light over a very, very broad spectral range. So like let's say from the blue all the way to the red and even more to the mid-infrared, for example, in applications in solar cells. So how would one find the shape of such a structure? Well, if you're a clever mathematician, what you can say is, well, what's a structure that has such a broadband absorption spectrum? And the sad answer is it's an infinite structure. It's just a metal sheet. So basically, if like this table here was made out of a metal, and I would place a molecule right here, this could excite such excitations in the metal all the way throughout the electromagnetic spectrum, basically. And now there's a mathematical trick called a conformal transformation, which basically just warps space. So like that's taken actually from something close to general relativity, if you wish. And that then, if you then just apply the right mathematical transformation, you can change the shape of this infinite sheet into something that's very small and very compact. In like this case, it's a crescent-shaped moon structure, such as this. And this will then have essentially the same light collection properties as such an infinite sheet, and can then concentrate light into very, very small areas. So one example where we want to use this now. This is a general statement that you can actually prove mathematically, that as soon as you have nanostructures that touch, you can get a broadband light concentration response. So here, for example, we want to make a lab on a chip for sensing of plastics explosives in the terahertz part of the electromagnetic spectrum. And for that, we need to have a metallic nanostructure, or like in this case, a semiconducting nanostructure, actually, that confines terahertz radiation over a very broad spectral range. And the way we do that is via creating such touching nanoparticles inspired by this. And then my very last message here will be that even though we work with light, we don't just work with light microscopes. Actually, one of the biggest tools of looking at light concentration is actually a transmission electron microscope, where you excite surface plasmons not with light, but where you excite these modes with an electron beam going by. Yeah? So also something where technology centers will certainly drive the evolution of this field. So here you see some transmission electron microscope images of triangles that are very closely spaced. So this from here to here is about 20 nanometers. And here you see images, direct images of the light concentration, which you could never do with a normal light microscope obtained in an electron microscope. Yeah, and with that, I want to finish. So as I've said, so we are already actually collaborating with Tomáš Šikola here, who is, of course, one of the leaders of one of the Ceitec areas. But I think, there's much larger possibilities for collaboration. So both from the hard nanophotonic sciences at Imperial College and also from biology. So I really hope that when the delegation that I've heard will visit in December comes to us, we can sign this and build a strong collaboration between our university and Ceitec here. And with that, I want to thank you for your attention. Yes.
Thank you very much for a very interesting presentation in plasmonics. And here is short time for a question. One question, please. It's very short time for for Stefan because his plane is nearly taking off. So no question? So never mind. Thank you very much.
I go to my next
yes,
now.
Thank you very much. And I would like to introduce a new speaker. It's Professor Button. A few words about his life. So, Professor Button graduated from University of Bradford. After this, he started with University of Sheffield as a research fellow. And after this, in 1988, he was appointed senior research scientist at Imperial Chemical Industries. He was a leader of group developing the radio frequency and microwave applications of thick film, high temperature superconducting materials. And in 1994, he joined the University of Birmingham, where is he now professor of functional materials and devices and leads a group with interests in a wide range of functional ceramic materials, processes and devices. Tim is excellent also in a special field of technology transfer because he established a new company. It's Applied Functional Materials Ltd. company in 2004. He is now managing director of this company, and he is currently developing and exploiting technologies for high-resolution ultrasound imaging transducers. And very important message as the last information for you. Tim will start, I hope, this November with us as a team member in the research program of advanced materials. So you are welcome, and floor is yours.
Thank you very much for that kind introduction. And thank you for the organisers for inviting me. and thank you for staying with it till this point in the program. My talk is going to be a bit of historical work that I've been involved in, a bit of a story of my research career, if you like, but also to really focus on the importance of collaborating with industry and technology transfer. I mean, why are we doing excellent science? We're only doing excellent science if it's actually going to be useful. And if it's going to be useful, we need to get it out there into industry. And I hope that's a focus that will come through from my presentation. So I'm going to say a few words about the University of Birmingham in an introduction. For those of you that don't know the institution, the main bit of my talk will be around powders, processing and products. As I say, that's really the focus of my research career. I will talk a little bit about the background of why that's interesting to me and why it's important, and also then focus on some successes and some highlights. I will then end, as everyone has ended, on trying to talk a little bit about how the collaboration with Ceitec can go forward. And it's a very exciting time and very privileged for us to be here, for me to be here. So the University of Birmingham, most of you will be aware, Birmingham is right in the centre of the UK, as far away from the sea as one can get. It's one of the older established universities, established in about 1900. It's made up of 5 colleges, of which I will... my school is part of one of those, and I will detail a bit more information about that. It's quite a large university, about 30,000 students, large number of undergraduates, and also a very high postgraduate population, large number of academic staff, and also academic-related staff. In terms of postgraduate applications, it seems to be one of the most popular postgraduate universities for postgraduate research in the UK. Apologies about the turnover figure there in dollars. I guess that's probably about around about €1 billion or so turnover per annum. So, as I say, quite large. In terms of Birmingham, Birmingham is about 2 million people, the whole area, so a bit bigger than Brno. And the university is a large employer in that area, and obviously contributes hugely to the number of graduates and postgraduates. As I said, I'm a member of the College of Engineering and Physical Sciences. That's made up of a number of schools or departments. This is a relatively new structure for Birmingham. We've gone through many changes. And now have this college structure. I guess the whole university is quite focused, certainly from the research side, on very strong links with industry. And one of the major industrial forces in the UK, Rolls-Royce, their main premises are actually not too far away in Derby, about 50 kilometres or so away. And we have very strong links with them across the college. This is what the campus looks like. We have a campus-based university. It's round about 3 kilometres from the city centre. It's all focused on more or less on the one campus site. I've highlighted here the main areas of the college and the various schools within the college. You can also see a very large medical school here and a hospital. This is a rather old photograph, and there is a new hospital that's been built on this site now over the last few years. I come from the Department of Metallurgy and Materials, and this is located just off this picture. So you can see it in this picture here. We have a academic staff of about 30, a postgraduate population of about 120, and about 40 research fellows across all areas of materials. Well, I guess it's fair to say that predominantly the research within the school is metallurgical. It's got a strong metallurgical background. But certainly my area of interest is in ceramics and functional ceramics, and we do our best to promote that area of research in what I do there. You'll also see that we've been in receipt of ERDF funding. The building here is what we call a net shape laboratory. This was built from ERDF funds nearly 10 years ago now, and again, puts in big facilities, big processing facilities, and aims to work very closely with industry. We are currently undergoing a large refurbishment of this particular building, our main building here, which is rather painful at the moment. We're having to move laboratories and do without things for a while, and always longer than the builders tell us that it will be. But I think in the end we will have fully upgraded facilities from when this building was built in the 1960s. It's really due for an upgrade. And as I say, we pride ourselves on our research background, and we have consistently very good research ratings in the UK research assessment exercise in its various guises. So that's where I come from. Now to the sort of main topic of my talk this afternoon. Powders, processing and products. Or perhaps I could rephrase it, research with a commercially orientated focus. You will have heard from the introduction that I had a spell in Imperial Chemical Industries, ICI, as it then was. And that really focused my mind on thinking that, yes, we have to do excellent science, but we have to get that science out into the world for it to be useful. So my whole philosophy now is to do things that I think or people think are going to be commercially useful. I want to take a step back now for you to understand where I'm coming from and talk about the problems in making things in functional ceramics. The first thing is that if functional ceramic is a ceramic or material that will produce some effect. So, for example, if you hit it with an electrical stimulus, then you might get a mechanical response in a piezoelectric, for example. And what you have to remember is that the strength of any, or the size of any effect for a particular material is really dependent on the volume of material you've got present. So, if you want a large effect, if you want a large actuation, for example, then you want a relatively large volume of material there. So, although thin film processes and nanotechnology is very, very important, it's the way a lot of things are going, there is still a role for being able to produce relatively large pieces of functional ceramic material in various shapes and sizes, if you want to produce a realistic, sizable effect. So that's really what I've been doing over the last 20 or more years. We need to develop processes where we can process powders into useful shapes or devices. And if we want to make things from ceramics, then we are talking about powder processes. The powder sizes could be around about 1 micron or so, but we need to produce certainly in hundreds of grams, if not kilogram quantities of these sorts of things. The problem is a bit more difficult because ceramics, as we all know, are brittle materials. If we drop a ceramic plate on the floor, it will break. If we drop a metal spoon on the floor, it won't. So ceramics are inherently difficult to work with, and that's another problem. So my philosophy has been that you want to minimize the amount of machining that you do to any ceramic shape that you want to make. So in other words, you want to make the material as near net shape, as near the shape you want it as you can. And that's really where my research has been heading. So we've developed a series of process routes. In fact, they're high shear process routes. I won't go into that this afternoon, but we've developed process routes where we can make a variety of shapes of different functional ceramic materials. So, for example, we can make tubes or hemispheres, which are useful as for things like hydrophones in underwater sonar. We can make very complex shapes, so things like helices out of ceramics. And you may ask, well, why do you want to make helices out of ceramics? But hopefully by the end of this talk, you will realize why you might want to do that. There are actual applications where that might be useful. So these are shapes that you wouldn't necessarily be able to machine. We've developed techniques where we can actually make what are called Biomorph devices. These are two-layer and multi-layer devices where conventionally they would be made in a planar form, but we've been able to make them into these very complex forms. And again, you'll see some more examples of what these are for in a moment. We can make molded shapes, so these sort of pillar shapes that we can make, and again, that'll come up later in my talk. We can extrude fibers. Fibers are very useful for providing actuation and integrating in fiber composite materials. And we're able to show that you can do that in a range of functional ceramic materials. We can make layered structures. We can integrate dense structures with porous structures to change the properties. And we can even make ceramic, very microscale ceramic components. This little gear, for example, is just a few hundred microns in diameter in a solid ceramic material. So this is very much the way that my research has gone, trying to make very complicated shapes, but useful shapes in functional ceramic materials. So what I want to do now is just highlight some what I've called technology successes. I've been very fortunate in most of the things that we've been involved in have actually been useful in some way. People have wanted to take them forward in various ways. The first one is some thick film technology. So these are ceramic coatings that we've developed of high-temperature superconductor materials. These produce very low losses and have been useful for cellular base station filters. And you can see here some of the sort of challenges that we've had. So the actual devices are usually three-dimensional devices, either these cavity-type structures or perhaps even this ring-type structure. There is a gap there that you probably can't see very well, but there's a gap in the ring as well. And so these have a ceramic substrate of some sort, in this case zirconia, zirconium dioxide. But the key property is the properties of this black superconductor coating on the surface. And we've had to develop techniques to be able to coat these films. These films are probably around about 40 or 50 microns in thickness. As I say, the key is in their properties. And this is technology that we developed in the UK and actually transferred to the USA. The second one is also a superconductor example, but a different application. And this is the application of high-temperature superconductors as current lead materials. So this is really exploiting on the fact that they carry current with no resistance, but they also have a very low thermal conductivity. So if you want to get the current from room temperature down to a low temperature magnet, then a high temperature current lead can go some way towards decreasing your heat loss. And this is work that we did with Yshapes technologies, and these are some of the current leads that we developed that were destined for CERN. So these are actually solid extruded materials. Here you can see a low TC wires that have been soldered on one end and a brass connection at the other end, a copper connection at the other end. These are slightly different. This is actually for a higher current lead where we've assembled a number of modules together, or assembling a number of modules together to carry a current. And one of these leads carried about 13 kiloamps. So a pretty sizable current for smaller pieces of ceramic. We've heard a little bit about solid oxide fuel cells. That's one of the interests that Ceitec has, or this aspect of Ceitec has. We did some work probably 5 or 6 years ago now, looking at particular problems of fuel cells, solid oxide fuel cells, with Rolls-Royce. And the particular slant that we had to think about was how to extrude this support module. So this is a honeycomb support module. And then how to print these electrode and electrolyte cells onto the surface of this module. So a bit of bulk ceramics technology as well as, again, thick film technology, but in a number of different materials. In this particular cell, there are 4 different materials that we have to learn to process together to make the cell to work. And again, to get a sizable, useful power from the fuel cell, you need that to be a fairly big unit. More recently, we've been involved in trying to make large actuation devices. So this is where you can produce a sizable actuation directly from a piezoelectric material. The piezoelectric response in most ceramic materials is actually very small. So normally you would only get an effect of a few microns. But if you process the material into the correct form, then you can utilize the geometry and the device particularly to your benefit. So these are Biomorph devices. So these are 2-layer devices, 2 layers of piezoelectric here with electrodes either side and electrode in the middle. And you can see if you wind it into a spiral, you get some rotation of a few millimeters. If you wind this spiral into a 3-dimensional shape, then you can get linear actuation again. And there's no scale on here, but this is a few millimeters. If you actually make a more complex device, such as the one here, this is still an all-ceramic device, but you can see it's now moving about a centimeter or so. So for those of you that think that ceramics are fairly fragile, yes, they are fairly fragile, but if you process them correctly, you can actually do some quite amazing things with them. And this is technology that's gone into a range of, or being looked at for a range of whole applications with a company called Cambridge Mechatronics. We've also been involved in making some fairly complex shaped ferrite materials for satellite communication applications. And this is an example of, these are called Yshapes for their obvious shape. They have holes in, and they need to be a very good surface finish. They need to be a very good density. And the ceramic ferrite materials are particularly brittle in terms of ceramic materials. So they are very, very difficult to machine once they're sintered. So these are devices that we've made and got the shape correct before we sinter, and then we sinter to a final density after we've got the shape correct. And these show benefit in terms of properties and in terms of costs and things for that particular application. So the final one is to talk about high-resolution medical imaging devices. And as was highlighted at the beginning, this is something that is very much ongoing. This involves making microscale molded piezoelectric ceramics. But I guess an alternative title would be the development of a Spinout Company. This is the technology that we've decided to take forward in the form of a spin-out company, Applied Functional Materials. And it's quite interesting that once one takes that step, we have a whole range of new things that we have to consider. So not only do we have to have good science and good technology, we also have to show there's a market need. We have to have some sort of unique selling point. Why would someone want to buy it? We have to have that competitive advantage. Why is it better than other things that can do a similar job, if there are such things? We have to show there's a route to market. It's no good if we can make it, but if no one wants to buy it and if we can't actually get it to market. So are we going to, for example, are we going to manufacture it? Are we going to license it to someone else to manufacture? Those are questions to be had. We have to show that we can do all this in some viable financial way. It's obviously all going to cost money to develop this, but in the end, hoping that we get investment, we have to show that there's a very large financial return. Otherwise, no one will invest in it. So it's really a very different set of constraints that we have to work within, rather than just doing science that is good. We have to show all these other things as well if we're going to get the company off the ground. And I would just want to show you a few snapshots of where we are with that sort of technology. So to start with, just a few words about imaging with ultrasound, medical imaging with ultrasound. This is something you'll all be familiar with. Everyone's familiar with fetal images, cardiac images, that sort of thing. Widely used, it's really the only safe imaging modality in terms of the medical field. And most devices on the market now will operate at a frequency round about 10 megahertz or so, between 5 and 10 megahertz or so. As with all things, where there's a frequency or a wavelength, the resolution is limited by that frequency or wavelength. So if we want to be able to image things at a higher resolution, we have to go up in frequency, down in wavelength. And this is really the driving force for what we're doing. Higher resolution medical imaging, higher frequency medical imaging. A number of different ways one can use the device for making an image. One can use a very simple single element device and then mechanically scan the device across what you're trying to look at to form an image. Or you can use a more complicated array transducer where we do this scanning electronically. And by far, most of the conventional images that are taken nowadays at the lower frequency, 10 megahertz or so, are done by an array transducer. That's the really established technology. What makes that transducer work? What makes the technology work? Well, it comes down to a piece of piezoelectric ceramic again. So something that I might be interested in. And this is a typical structure that one wants. So pillars of piezoelectric within, in this case, a polymer matrix with an electrode on the surface. At lower frequencies, you can make this device by machining. At higher frequencies, then really the brittleness of the ceramic, the size of the elements that you want to make comes down to 10, 20 microns or so. This gap becomes less than 10 microns. It becomes very difficult, if not impossible, to machine. And so what we've developed is a molding technology. So this comes back to one of the areas that you saw at the beginning of my research career. One of the net shape things that we've been able to do. So we start with a powder. We mix it in some way. We mold it into a mold. We then demold sinter. We end up with these sort of pillar structures, which we then encapsulate and then lap and polish and put electrodes on. And there is our device. In our particular case, though, what we're interested in is making pillars of this sort of structure. So these are about 20 microns in size, about 120 microns tall. So these are structures you probably couldn't machine very easily, or impossible to machine, we think. You have to make them by some other technique. But the molding also opens up some new exciting areas. This is what we've called a random structure. So this is still a pillar type structure, but randomized in its sort of latitude. And this gives some increased properties or better properties for the device. And this is a patented area of technology that we think is key to what we're trying to do. Of course, we have to make good materials. We have to do good science, good technology, and so we have to characterize our materials. This shows a resonance from one of the devices, and also some calculations based on that of some of the material properties, and some comparison with modeled materials. We have to take those composite devices and actually put them into transducers, so we have to learn how to do that. And these are single element transducers that we've manufactured, where we've shown that we can do that, and we've actually managed to sell some of these devices as well. We have to show that people actually want what we're trying to do. And high-frequency ultrasound, it's an emerging market, and the message really is that although the ultrasound market is established and but still growing, actually the emerging area of high-frequency ultrasound is still a very large market to go after itself. And you can see some examples here. This is high-resolution images of the skin, where you can see you get a lot of detail in using these high-frequency devices, as well as potentially ophthalmic applications as well. So we have to show that we can go after that sort of market. We have to learn how to make array devices, and therefore we have to learn how to make electrodes. We have to learn how to pattern electrodes on these complex materials, and we've now done that in a prototype way. And we are very much at the stage when we believe that we can take this forward, but we are in the sort of latter stages of talking with potential investors. So it's a very, very different field than just doing the science. Actually taking it to the next step is actually, in many ways, much more complicated. I want to finish with a little bit about collaboration with Ceitec. The interest from Birmingham and the interest from me. There is a historical track record of collaboration, certainly between Brno University of Technology and Birmingham, before my time, but it is there. I would also point out, as everyone has said today, that really collaboration is essential for all of us in the present world. None of us can really do things ourselves anymore. We have to collaborate to make things work. I see the very broad Ceitec remit as actually being very encouraging, certainly from someone such as myself who works in materials, but actually the application of what we do is actually much broader into the life sciences and medical and things. So that's, I see as very, very important. I think there are many future possibilities. As Professor Ruber mentioned, it is hoped that if the mechanisms can be sorted out, and I believe that it sounds like they are being sorted out or have been sorted out, then certainly I plan to spend a lot more time here as well as back at Birmingham and help to cement that collaboration and for the benefit of both Ceitec and Birmingham to take this sort of work, the sort of functional ceramics work, forward. So I'll just put up the summary there, and really just thank you for your for listening. Thank you for still being here, and I very much look forward to a continuing interaction with Brno and with Ceitec. I'll just end with some acknowledgements there. Obviously, most of the work that I've done is done by my students and postdocs, and I'll leave that up as a final point. So thank you very much.
Many thanks, Professor Button, for a short visit to University of Birmingham and a wide overview of your research and technology transfer. Maybe a very short time for one question. Yes, please.
Probably give us around about 30 microns or so, sorry. About 30 microns, yeah. But it's really, it's wavelength dependent. So.
Any other question? No. So thank you very much once more. And maybe I can continue in Czech. Mám tady jenom upozornění. Máme teď ten program zase rozdělený na několik větví. Ti z vás, kteří chtějí navštívit zdejší laboratoře, mají zůstat v této aule. Ti, kteří chtějí navštívit laboratoře v ostatních institucích, to znamená na VUT, Mendelova univerzita nebo Výzkumný ústav veterinárního lékařství, tak mají několik minut, aby nastoupili do autobusu, které stojí před touto budovou, čili před univerzitou. A jinak můžete přestoupit na českou větev přednášek, které pokračují v malé aule. A večer buď to slavnostní recepce 17:30 až 22, anebo ti z vás, kteří mají objednáno divadlo, mohou v 18:30 se nechat přepravit do divadla, které začíná v 19 hodin. Takže děkuji a končím dnešní odpolední sekci. Díky.